Hello, this is Alistair Plotnick with the Lab 4 for Physics 2212, Summer 2024. So first, the introduction and purpose is to use a model of a barred magnet falling through a metal tube to create a better understanding of Faraday's law and develop a computational model of Faraday's law from this experimental data. So first, the basic model used in this experiment is the Ballard-Swart law for a B field, Faraday's law, and Newton's second and third laws. So a quick preview of the results is the time for the magnet to fall from the experiment was 1.26 seconds, and the time for the magnet to fall computationally was 1.348 seconds. So our experimental procedure is a magnet north in the barred magnet was established using a magnetometer and the Firefox app, and then the barred magnet was dropped through a tube of aluminum foil in order to get time readings. This dropping was repeated 5 times in order to get a better estimate of the average time, and here's a picture to the right of what that experiment looked like and me dropping it. So our measurements is the length of the aluminum tube foil was 0.3 meters, the width of the aluminum foil was 0.006 meters, the inner radius was 0.02 meters, and the radius, outer radius was 0.032 meters. The mass of the magnet was 0.024 kilograms, and the average fall time was 1.26 seconds. The magnetic dipole moment of a bar magnet, which I used from the previous lab, was 5.384 joules per Tesla. So the checkpoint questions, why can't we use a ferrous tube? A ferrous tube has iron and thus could become an induced magnet, which could affect the falling of the magnet. And what happens to the magnet? The magnet falls more slowly through the tube, and then it would be in free space, allowing for the catching of the magnet. So here are my details of the coding. First, setting the constants to what they were, as well as from a previous lab as well, the mass and the mu, and then here's a function calculating the deflux here, and then continuing on with the further steps of calculating setting it equal to the force of gravity, and then solving as well for setting F net equal to F grav and F magnetic and solving. So here's just a computational readout of what it looked like before versus what it looked like at the end, the red being the counterclockwise and blue being clockwise. And here's also the velocity versus time graph. So in interpreting the simulation questions by Lenz's law, the red from the model is the counterclockwise and blue is the clockwise because this slows the magnet down. And then a flip magnet would just have the same, have the current flowing in the opposite direction, but would have the same results. And the computational model is close to the experimental model, but it could be improved by splitting the tube up into more rings or factoring in air resistance. The shape of the velocity versus time graph, the forces are unbalanced when the velocity is increasing or decreasing, but balanced for about a second in the middle of its descent, and you get, yep. So what if the resistivity of the conductor was reduced to as close as possible to 0, how would the dynamics of the falling magnet change? The braking force would increase to a point where the force of the magnet can counter the gravitational force and prevent the magnet from falling through the tube at all, and therefore it would kind of be levitating at the top. And then what if the holes or slots were cut into the tube, and how would this affect the ring current in your model? So the number of rings in the model would decrease, leading to an induced current and a reduced magnetic force. This would decrease the time that it takes for the bar magnet to fall through the entire tube itself. So coming to our conclusions now, the experimental time for falling was 1.26 seconds, and the computational time for falling was 1.348 seconds, and the code will be linked in the description for the video. And the difference is due to some human error in my recording during the experiment, or with how fast I recorded the times. There could be some human error just hitting the stop button as immediately, or more likely calculations of mu from my lab too. But however, the computational model was close to the experimental model, meaning that it did model Faraday's law somewhat accurately. And that is all for this lab.